So hello, my name is Scott Fadden. I'm with IBM. I'm with the IBM GPFS development group. My job is not development. My job is to work with the people you've been hearing in the last couple days to implement the next biggest system, the next biggest storage environment. And Addison, I like your question about what is Exascale, because I've been asking myself the same thing for, ever since I started seeing the term show up here and there. And really, to me, I kind of came to the conclusion that Exascale isn't a target, but more of a direction. It's kind of like any other buzzword out there in the industry, right? Whether we started with clusters, then we went to grid computing, then we went to on-demand, and then we went to cloud, and so on, right? To me, it was all the same thing. It's okay, I take what I have, let's make it bigger, better, stronger, and so on. So what I want to talk about today is a couple things. First of all, kind of my vision for what we have to look at to be able to do exascale storage, whatever that means, right? Is it exabytes, is it exaflops? I don't know, but I know that we understand very well some of the challenges today that we're seeing already at the scales we're at, and they're only going to get more and more complex, right? That is clear. The rest of it, I don't know if it's so clear. So I broke it down very simply. I mean, the challenge is this, as these things scale up, and I'm thinking, today, my job is to implement what we have today and to help development find what we need tomorrow, 5 years from now, or 2020, depending on who you ask when we get this first exascale system, right? The first thing is obviously reliability. We've had a lot of discussion around how you make something like this reliable. When you're talking about hundreds of petabytes of data, nearline data, I'm talking about directly accessible data. Now you have RAID reliability issues, even with larger drives and so on. But you've also got infrastructure reliability issues, right? So you can't just think about the disks. You have to think about paths to disks, about where data resides, how I can get to it, things like replication, things like security, right? So we've been talking a lot about performance, about keeping it up and keeping it accessible. How about encrypting data? How about encrypting data paths? How about securing my data against attacks or for open? Because a lot of this goes, kind of as we work our way around. John just mentioned that, one of the things that's a challenge today in performance is balance, right? If you have one OSS or one OST that's slower than the others, it's going to slow everybody down, right? So how do we address these things in performance? We know today that it's very, very difficult to assume that everything's always working, right? We like it to be, and we like it to be for acceptance tests, certainly, right? But it isn't always there. So we have to find technologies that detect these things automatically, reroute requests, keep data local, all these sorts of things to make this actually work. Cost, of course, always comes in there, right? We need to reduce costs, we need to keep things. That's the whole point of this, is to do it at scale, to do it more efficiently, so we can keep costs down, so we can keep the environment working more straight ahead. And I put two words on here that you don't normally see on presentations like this, and I went round and round on how to describe this. Came up with intuitive and visceral, right? Now it's kind of a strange word, but the idea, and what I'm trying to impress on our team, is that we need to automate things. We need to make things natural. We need to make them obvious, right? We can't look and say, well, if that goes down, okay, we're slower. We have to look and say, well, I'm an application developer, I'm a scientist. It doesn't go down. I just want my job done, right? I want my thing to complete, whatever it is. So we need to have an organic approach, a natural approach to solving these problems and to solving the infrastructure issues. It's not just about neat new hardware. And I think all of this comes around to how do we solve this, and we're going to end up solving it in software. Because the best piece of hardware in this infrastructure is just one piece of the puzzle, right? You can have the best network switch, you can have the best storage, you can have the best server, but if there's a problem with that piece of it, everyone else has to deal with it. And one thing we know for sure in these systems, there's always something wrong, right? I don't care what system it is. So we talked about a lot of the different storage devices and the ways we do storage. there's really different classes of storage. It's solid state, however you want to do it, whether it's flash and VRAM or some other storage technology that's coming in the next 5 or 10 years. You've got spinning disk, which we don't see going away anytime soon, and we had some of the challenges around that. We certainly have long-term storage, and I left it called long-term. We don't necessarily want to say tape. It could be the infamous cloud or whatever, I don't know, right? But we have to think about long-term storage. We have to think about how we keep this stuff around, and we have to think about how we interact with other sites, because that's a storage challenge as well, right? It's not just a matter of keeping it on disk or putting it on tape or being able to get it back when I want it or getting it the right place when I want it. What if I want to do things at other sites? So I kind of broke this down into what I consider data realms or data domains. I couldn't come up with a really good word for it. But we have to think about this problem, the problem of managing data at Exascale at all the different levels. Right? It's not going to be a simple solution of the best storage. In the node, right? How do we use data in a node? How do we get data to and from a node? How do we get data to and from GPUs and other special processing technologies that are going to be coming in the next few years? Right now that's a challenge today, right? We have some workarounds, we have some ways to do it, there's better and worse, but we have to look at that. We have to look at how we're getting data to where it needs to be. In a node is certainly it, and I think it was Mark talked about yesterday that we're not going to be putting disks in all the nodes and doing burst buffer, for example, right in the nodes. It's just not feasible. So maybe we need to think about what's nearby. The concept of data locality, data awareness is key to this solution, right? It's much easier for me to send a job somewhere else than to send data somewhere else. It's much easier for me to make sure the data is there before you start using those CPUs so you're not wasting time waiting for I/O, right? That's the constant battle, right? The compute guys are always looking at us I/O guys saying, you're slow, you're slowing us down, you're wasting CPU cycles. And we keep telling them, well, give us more information about what you want to do. And this is what comes into intuitive and visceral. We need to make the system understand better where the data needs to be, when it needs to be there. Today, we're already doing some of that. We're working on data aware types of operations. I'll get to that in just a minute. We have the concept of directly accessible storage, right? Today, it's typically spinning disks, sometimes SSDs, and so on. We need to keep that in the realm of nearby and in node. Well, more nearby, right? What is directly accessible? How do we access that disk? And how do we interact with the long-term storage? So, and there's also working across sites, right? So if I want to run a job at another location, or if my data exists in another location, one of the things, so at IBM and GPFS specifically, we have thousands of customers in all different industries, right? So we don't look at this only from these top 50 or top 100 biggest machines we've been talking about here. We look at it for everything, right? And everyone wants to start sharing across the world, start moving, part of the job happens here, part of the job happens somewhere else. It's no different here, right? You may have data and they have a type of machine you want to run that on, you need to get it there, you need to use it. Again, it needs to be intuitive, it needs to be built into the system. So I want to talk about kind of what we're doing today in these areas, where we're at, where we're going, and how we're going to be putting this all together, or at least how we envision it today. Like I said, my job is to take the tools we have today, put them out in the world, see how they do, and I have direct feedback. In fact, I'm spending the next 2 days at research talking about these topics so we can get these new features up and running and usable for you guys as quickly as possible. So I put platform LSF at the top. I don't know how many of you know, it's a very, very simple definition. It's a scheduling tool, right, for jobs on a cluster. I put that first because when we talk about data, people always think about disks and storage and file systems, and I certainly like file systems, right? That's my job, but there has to be other pieces to it. We have to have other layers that are taking care of pieces where maybe the file system doesn't make sense, or maybe physically moving the data doesn't make sense, and that comes into the scheduler. The scheduler not only has to understand what machines are available and how many CPUs and memory they have available and power and all that kind of stuff. Certainly a whole field of discussion we could have. But from the storage aspect, it needs to understand, it needs to start learning what storage, what data it can get to. So you have to start thinking of it as data and not just as storage, right? Right now, we kind of take a brute force approach, right? Our brute force approach is, let's throw all the disks out there, let's give everyone access to everything, stand back and just get what you need, right? Well, that doesn't scale. I can tell you from personal experience and many, many hours at many customers, there's a lot of challenges in that environment, right? We can do it, and we do it successfully every day, but there's also challenges every day, right? So we can start leveraging things like scheduling tools. If they understand the data, if they understand that part of the data set's here, part of the data set's there, they can send the compute job to the cores, to the data. Now, this is kind of Hadoop-like, right? I mean, we were talking a little bit about big data yesterday and what is big data. And I'm not saying that all big data is Hadoop or, you know, the point is that the idea of Hadoop is a neat one, but we don't have to limit it to disks in a node. What if it's disks in a rack? What if it's disks in a room? What if it's disks in a city? We have to take that idea of locality and move it into the rest of the environment to make things more efficient, because as much as we'd really like to, we can't defy physics, right? We still have a certain amount of data. We have to get it from A to B, and if we have faster links, great, we can get it there faster. If we have, you know, bigger disks, we can get it there easier, but we still have to get it there. So we have a number of other technologies, and these are all released technologies, by the way. I'll talk about where we're at today and where we're going with these. A number of technologies we have today that we're already doing this with is, first is called active file management from GPFS, right? And the idea there is to get data where you need it, when you need it. So I'm going to talk also about some work we're doing with Argonne National Labs. We're doing some research on what we call burst buffer-like, right? I'm not saying it's a burst buffer, I'm not saying it's everything we want, but again, we believe in a step-by-step approach, right? And we're actively researching how we can use active file management, which is a caching technology, to implement and move data automatically between tiers of storage. So just to give you a quick background on the environment we're working with here, because I'll use it without thinking about it. We have the Mira system, which is, as Paul mentioned, is 768,000 cores on Blue Gene Q. Right now it's connected to, let me see if I get my numbers right, 16 DDN12Ks. We're adding into that 30 IBM GPFS storage servers. And we're going to be using this GPFS storage server-based storage, and I'll talk about this all in a minute, as the cache, if you will. This will provide a number of benefits today, and hopefully in the future will allow us to do more and interesting things, right? Today it gives us things like availability, right? So what if a whole cluster goes down? As much as I like to think GPFS is wonderful and perfect, things happen, right? If a whole cluster's down, how can we keep jobs running? That's the whole point, is to keep science moving forward, right? Let's not waste that CPU time. We can use AFM for that. We can use the ability to move data into this cache, if you want to call it that, for the time, 8 petabytes I have a hard time calling a cache, right? It's a really big hunk of cache. We can move the data into there. We can destage it when you don't want it. We can get it before you need it. And we can do it smartly, right? So for example, we were talking about rebuild performance and things. How about, in this kind of environment, what we're doing is instead of saying, well, all right, let me throttle this back, have the software automatically do it, right? So when you go to checkpoint, we just get out of the way, right? Stuff like that. That's the kind of intelligence we need to build into this infrastructure. So that's AFM, and that's already been shipping for a year or so. We're constantly adding features to it. And I think this project we're doing with the National Lab will really help us move forward on it as well. Another technology that we've had out now for a few years is GPFS Storage Server. It's come out in a few different flavors. I won't go into the whole declustered array, you just had that talk, right? Slightly different approach, but same idea in the sense that you have to solve the performance problem, and the performance problem is things are going to be failing and disks are bigger, right? Very simple. We're able to take the GPFS storage server, deploy it very quickly. A couple dimensions of it that work really well in HPC that we hadn't seen in the past, and as a guy who has to implement a lot of these things, makes me very happy. One thing is I don't have to carve out certain arrays. I just use a pool of disks. There was no tuning. The last deployment we did in it took 4 weeks, but we only got 1 day a week to do it, so I'll say we did it in 4 days. right? Worked right off the bat, we got some network stuff figured out, and we were running, right? We only used half the storage. We were able to use the other half of the storage for test and development. Rebuilds are less than a 2% impact, and full rebuild performance, if you lose multiple drives, takes about 15 minutes to do what we call critical data recovery, right? And we actually ran those tests under load, right? So we ran them with a full IOR, running on a system about 400 gigabytes a second. We were able to pull drives, and things worked really well. We didn't even notice. In fact, they were toying with us because I was working remotely. They were pulling drives while the run was going, and then they asked me afterward, did you notice? And I didn't until they started pulling multiple drives per disk, right? So GPFS storage server, we certainly have a lot of work to do there. We can make it more intelligent. Today it detects things like, hey, there's real I/O coming in, let me get this maintenance work out of the way. You know, that kind of thing it does automatically. We're doing checksums end to end. We've got to make sure that data is there consistent, right? Because we got wonderful networks, we've got wonderful machines, but things happen, right? Physical media has issues. So we have to pass that data all the way through. This again goes to, yeah, all right, so we have the RAID rebuild part figured out. That works really well today. Now let's take it to the next step. Let's make it more intelligent. Let's introduce things like I said, the ability to check some data all the way through. How about the ability to detect that you're running slower than everybody else and to get out of the way? These are the kind of things we have to implement to make this stuff usable in this very large environment. I'll call it the Exascale environment since it's this conference, right? We can even take other technologies. When we're talking about locality and data regions today, we have what we call file placement optimizer. And it's a strange term for basically, its original intent was to use in replacement of HDFS, right? Very simply for Hadoop MapReduce workloads, right? So you put disk in a node and we can send data to the right node and keep it there and put it in chunks and all this sort of thing. Yes, we can do that today and we're shipping that today. But we can also take this technology again and it's a disk. Why does it have to be a disk in a node? Can it be a disk in a rack? Can this locality be within a region or a section of my data center or on a subnet? Again, all these things work today. We're just finding different uses for them. We've been talking about these technologies for a couple of years, and actually we're really realizing the benefits today. All of these are in production at different sites, relatively large sites. All of them are growing and growing in popularity as well as market share. So we've done a lot of this to work toward the Exascale vision, right? And the Exascale vision is this really, I have my job, I tell my job to run, it runs on the right machines, it gets the data where it needs to, and we're off and running, right? Goes back to that intuitive part. So, oops. So where are we at? What's next? Today, we're delivering this all, we're doing the research with Argonne. If all is successful, it's research, right? We'll get some things, we won't get some things. But if all successful at Argonne, we'll be able to have multi-tiered storage, automatically moving data between tiers. This sounds very similar to what we've been talking about with burst buffer, right? Because the software, once it has the intelligence to move the data back and forth, do it at the right times, put it in the right place, what does it matter if it's an SSD, and VRAM-based storage, some other type of memory storage that comes out in the future? It's all the same thing, right? It comes down to the software, having the intelligence in the software. So that's really all I had today. Does anybody have any questions? Yes?
How does this picture change now that x86 is going over to Lenovo, part of GPFS and things like that?
So the question was, how does this picture change because of the Lenovo sale of the x86 business? It really doesn't. And in fact, it fits right into it. GPFS today runs on non-IBM hardware at a lot of places, right? Thousands of different machines. And so IBM's picking the software business, right? This is our core business. This is our core thing. We see the software as being the key and the hardware as being the tool, right? So for us, it works out just perfect, actually. And GPFS stays with, GPFS storage server, Lenovo will be selling that, but we'll have other versions of it out as well. And also, there is a, can't talk about non-release product, right? But there's a release future for more interesting things along the RAID area. So watch that space over the next year and a half. Again, software. The big focus is to use other buzzwords. You know, you got to throw in a few buzzwords here and there. Software-defined storage, and I believe IBM with GPFS has one of the key software-defined storage solutions in the industry.